I'm not good at physics. I am just doing this for a school project. If anything is wrong, correct me.
Don't ask why, but this is being done in a closet. Look around you. Zoom into any object. Just imagine that in your head for a second. Like, take this coat, for example. This thing is made of atoms. And those atoms are also made of other parts, electrons and a nucleus. And that nucleus has even more parts in it, protons and neutrons. And guess what? Yes, those are made of other things as well, called quarks. Now, quarks are part of the Standard Model, and the Standard Model is the basis for which everything is built upon. But this kind of leads to a big question. What are those made of then? And why is this even a question? Doesn't the Standard Model cover absolutely everything? Well, here I present to you the problem, but first, to understand that, you'll need some background information. So there are 4 fundamental forces of this universe, and in the Standard Model, there is one particle that carries each of those forces. Photons, which is one of the particles, carries the electromagnetic force. Gluons, which is another, carries the strong force. And then the W boson and the Z boson carry the weak force. And now there's another force, which I know you've all heard of, let's be honest, gravity. But there isn't really a particle in the Standard Model that's carrying gravity. Well, this is because in the quantum world, Einstein's theory of general relativity, which is the basis for gravity, kind of falls apart, and so does the math. In the quantum world, things just don't behave as they should. And while Einstein was making a theory, he wasn't too concerned with little quantum particles. He thought more of gravity as a fabric being warped by mass. Okay, so the point I tried to make with that but never actually arrived to is that when you try to include gravity into the Standard Model, the math no longer works. And we also don't even know what the particles of the Standard Model are even made of, like quarks. What would that be made of? And we can try to observe it using, light rays, but the light rays we use to look at these kinds of things, they're way too big to look at tiny things like quarks. We can try to solve this problem by creating high energy waves, which are smaller, and they can look at the particle, but then because they're higher energy, they alter the particle. There's really no way of getting what the particle actually looks like. This is kind of similar to Heisenberg's uncertainty principle in that you reach a limit on what you can know about a particle. So quick recap, the problems that string theory is trying to solve is the inclusion of gravity in the Standard Model and what the particles of the Standard Model is made of. So then, with all these problems, how are we solving them with string theory? Well, string theory is the idea that all particles in the Standard Model are made of vibrating strings. Like how on this undersized violin, different vibrations will make different notes. Different vibrations of filaments will make different particles. Seems simple enough to me. Well, then how does all of this solve gravity? Well, scientists did what they do best, math. And using that math, they made a hypothetical particle that would carry gravity called the graviton. And they were able to calculate some of the properties of this graviton. And in string theory, there's a specific string that actually matches some of the properties of the graviton. But what's even crazier is that string theory was not built around gravity. Originally, it just came as a way to explain hadrons in a particle accelerator. Gravity just came out as a natural result of the math in string theory.
String theory not only solves gravity, but it proves some interesting ideas to be true.
So one cool thing that string theory actually points to is that the fact that there are at least 6 other dimensions. Now this isn't exactly a deal breaker for most scientists. In fact, they've figured out some ways that this could be possible. One of those ways being compactification, the idea that all these extra dimensions are just so small that we're too big to access them and that we can't understand that dimension because we're too big. But there's more that string theory implies. If string theory is true, then the principle of supersymmetry, one of the principles string theory is built upon, should be true as well. And basically what supersymmetry shows is that there are more particles in existence than we think there are. And string theory is based on the principle of supersymmetry because supersymmetry makes the math possible and makes it a lot easier because items can cancel out because of that. So if string theory were true, that means there are supersymmetric particles out there that we haven't seen yet. I have to talk about this, okay? I spent too long researching this. Okay, well, fermions have half spins and bosons have integer spins, and that's what categorizes them. And what supersymmetry suggests is that instead of just the Standard Model that we know today, there's a whole other set of particles, basically twice as many as we thought there were originally. fermions have half spins and bosons have integer spins. In supersymmetry, there's a whole nother set of particles with spins that differ by half. And so that means the fermions with a half spin in the original standard model will suddenly become integer spins, which means that they're bosons. And bosons here, with their integer spins, will have half spins in their cousin particles. And that means that bosons and fermions have a special connection that might be possible. And basically all of this means that there's really twice as many particles that we think there are according to supersymmetry. Not 18, 36. But supersymmetry right now is all hypothetical because, none of this has really been proved. However, physicists have theorized some reasons why these special supersymmetric particles can't be found anywhere. One theory of which being that these particles are extremely high energy vibrations. And so maybe they're around in the conception of the universe when, the universe was still extremely hot and expanding greatly. And as the universe expanded and cooled, these very high energy vibration supersymmetric particles slowly cooled down into lower energy vibrations, aka other particles. If the principle of supersymmetry is true, it already solves a few problems in and of itself. One of which being Higgs mass. Higgs is a very large particle, and supersymmetry gives the ability for scientists to cancel out any additions to Higgs mass, which makes, a less obese Higgs. Supersymmetry also solves dark matter and what it's made of. Right now, we don't really know what dark matter is made of, but scientists are thinking, hey, one of the supersymmetric particles have similar properties to dark matter. And so that means if any supersymmetric particles are found at all, we know what's in dark matter then. String theory has some setbacks that even, the most proud string theorists aren't too happy with. The first one being that they have to assume the existence of many particles, many. They have to assume the existence of 18 extra particles. String theory failed to predict the accelerated expansion of the universe and failed to even make sense of dark energy at all. And lastly, there are many different variations of string theory that are mathematically sound, and I am talking many, many. So if string theory was true, then which one? Even if string theory was mathematically thought out to the finest detail and perfectly made sense and just complete, there needs to be some way to test it. And so far, no one really knows a way to test string theory. Another digression for your brain. While working on string theory, existence of dark energy and the accelerated expansion of the universe just suddenly popped up. And this was kind of uncalled for because string theory didn't hint at dark energy or the acceleration of the expansion of the universe in any sort of way. String theory didn't know that this was going to happen. And when they used the best theories to try to calculate the amount of dark energy seen by astronomers, the numbers failed to predict it at all. In fact, they were too large. So string theory just failed to make any sort of sense out of dark energy. Now this, for some people, isn't really classified as a flaw of string theory because no other theories at the time hinted at the existence of dark energy, so why should that be expected of string theory? But some physicists say that string theory, since it's redefining gravity and flipping gravity on its head completely, they expected string theory to maybe point at dark energy and expansion of the universe in some sort of way. Years after dark matter was discovered, it was found that string theory could actually be modified to include it mathematically. The critics aren't really satisfied, but the string theorists chalk this one up as a win. So, after learning all of this, what are we supposed to gather? Well, the universe is very complex. The fact that, 7 billion people are working together at the same time to make sense of this universe, and yet not one still knows the true nature of it, it's pretty amazing. So then, maybe the world isn't as simple as a bunch of vibrating strings? Or maybe it is. But what we do know is that the universe and its laws are very purposeful and interconnected. Change any one small law governing this world and life and the universe goes poof. It just basically ceases to exist. So I want you to look at something. Anything. And I want you to think, what's it made of really? And why does it behave the way it does? It's questions as surprisingly simple as these that can help get us, just a little bit closer to understanding the true nature of the universe, whether it be vibrating strings or not. There are 4 fundamental forces of this universe. And we can try to solve this problem by, shrinking the light ray into a higher energy. Wait, that does not make sense. Oops. The standard model and that means the fermion spins and that means the fermion spins. Oh my gosh.